Okay, so hello and welcome back. Basically, the next example is example number 33, which is show that the basically this is basically this notation over here does denote the max function, and I'll tell you a little bit about the max function in just a few moments. So the max basically from this set to this set, meaning that the max function on the set of real numbers given by a comma b to basically max of a comma b, and the min, and this is the min function. As you can see, the denotation is like the logical and or, for example. This is the min function over the set of real numbers given by a comma b to basically the min of a comma b are binary operations, right? So first of all, this max function, you can use it. Of course, you can. It's pretty. The notation can be used in many different ways, and you can use it for arrays of numbers, arrays of letters, and so on and so forth. And the function takes a set and an index, meaning that takes some you could say it takes some set, meaning that when you write basically max of, and here I'm using parentheses, normal parentheses, max of x, for example, comma I. This x is basically an array of numbers or array of basically letters that contain some elements, and then this I is the index, meaning that you can choose from different indices, meaning that, and then this returns something, right? Now, but normally what you can do is that I'm assuming that based on the notation that they have used here, normally what you should do with this function, if you use it with square brackets, then you can basically leave out the index and then just and then just write all of the elements over here and then evaluate the function, meaning that, for example, if I omit I here and use simple square brackets, I can use max of, for example, 1, 2, and 3, and then this returns the maximum of these numbers, or the largest value in this array, which gives me a 3, right? Or if I write, for example, by the same logic, if I write the min of 1, 2, and 3, then that gives me a 1, right? Now, I'm assuming that, and I don't really know because I couldn't anywhere find this notation using curly braces. I'm assuming that they have used the curly braces interchangeably with the square brackets. And so based on that, what I will say about this function is that this is the same basically max and min function, and then your a and b are your arguments. For example, the max of based on what the way that it's been written over here, the max of a comma b is the same thing as, for example, a, if, for example, if a is greater than b, for example, you could say. Or you can say that the max of a comma b is the same thing as b if b is greater than a. I suppose that's how we can understand it here. Now, what we need to basically, we have the max function as a binary operation on the set R, which is basically given by this rule, and we have the min function on the set R as a binary operation given as this, and you want to show that these are binary operations. So of course you know that the set of real numbers is basically the Cartesian product of the set of real numbers is going to be r times r, and then you will get a bunch of elements like, for example, 1, 2, 1, 3, and for example, I don't know, 1, for example, 3.1, and so on and so forth, right? And then if you pick any of these ordered pairs from this set and evaluate it this way, meaning that if I have 1, 3, for example, and then the max of for example, I can write the max of, now if I write basically 1, 3 here, if I write 1, 3 here, then that gives basically the max of 1 and 3, which is equal to 3. If I have 3, 1, which also belongs to the same set, that gives me the max of basically 3 and 1, which is again equal to 3. That means that basically if I take this as a function, let's call it, for this time being, let's call it f, for example, then f of this input is equal to 3, and f of this input is equal to 3 as well, meaning that the function actually becomes a many one function, but still it is a function. We have no problem with that being a function. And the min also is basically the same story, meaning that if I have, for example, the same story here, if I take, for example, any of these elements, then taking this part into consideration, which is basically the min r times r to r given by a comma b, basically gives the min of a and b. Then if I take, for example, 1, 3, that means that I have the min of, for example, 1 and 3, which gives me a 1. If I have 3, 1, again I have the min of 3 and 1, which gives me a 1. Again, this is mapped to this one, and this is mapped to this one, and so still it is a function. There is no problem with it being a function. So as an argument, and again, although what I'm doing here is that I'm simply explaining the situation to you. I'm not proving anything here. So you're not supposed to take this as a proof or anything. This is actually no proof, because I have just given you only a couple of examples. More than that I have not done, really. So now this is the, since you can say, as a solution, you can say that since basically this is the max function, since max carries each pair, a comma b in basically in the Cartesian product of r and r to a unique element namely maximum of a and b, namely maximum of a and b, lying in R, and also since well, I got ahead of it. So and since that is the case, then then basically the max function is a binary operation, on the set of real numbers. Use the similar argument. When using the similar argument, using a similar argument, one can say that basically the min function is also a binary operation. On R. Okay. Now, as a remark, we have so this is the max. So the max of 4, 7 is the same thing as 7. Of course, normally you shouldn't actually, you should use the notation, right? Of course, what I'm saying is based on only one source. I'm not really sure about that source, but it seemed to be trustable. There was a website on the internet that I read this information. Based on that source, this notation is actually not right, meaning that when you write the maximum of 4, 7, then this 4 represents, well, let's not talk about that. It's as far as we understand that this notation right here denotes basically maximum, and then as far as you understand that whatever you have these, and as far as you understand that these two are arguments of the max function, and what the max function does is that it compares those numbers and it returns the largest number. That's basically, as far as we understand that much, I think that's more than enough for now. Okay, so about the remark, we said that the max of 4 and 7 is equal to 7, and the max of 4 and negative 7, and the max of 4 and negative 7 is of course equal to 4, right? And also you know that the mean of 4 and 7 is equal to 4. The mean of 4 and 7 is equal to 4, and the mean of 4 and negative 7 is equal to negative 7, right? Which means that but of course that means that basically this element will be mapped to 7. This element will also be, and these two distinct elements will be mapped to the same element, and so on and so forth. Now, when a number of elements in a set A is small, we can express a binary operation star on a set A through a table called operation table for the max of 4 and 7 is equal to 7, and the mean of 4 and negative 7 is equal to 4. I think I made a mistake here because I didn't get the point. So here what they have written is that the max of 4 and 7 is equal to 7. and the mean of 4 and negative 7. 4 and negative 7 is equal to 4, and also this is actually the max, I'm sorry. So the max and the max, okay. So, and then we have the mean of 4 and 7 is equal to 4, and the mean of 4 and negative 7 is equal to negative 7. So now I don't get the point why they have written this over here, but then the rest of the text says that when the number of elements in the set A is small, we can express a binary operation star on the set A through a table called operation table. So basically, when the number of elements in a set A is small, we can express a binary operation star, on the set A through a table called basically operation table. Right? Now, for the operation star, for example, consider A is equal to 1, 2, 3. Then the operation max on A defined in example 33, which was basically this example here, right? This example over here, can be expressed by the following operation table. Can be expressed by the following operation table. Now let's see how the table is made. So you need a table something like this, and then you have 1, 2, 3, 4, and 5, and then something like this, and this is and, I'm sorry, not and, but and actually would be something like this, but we are not talking about logic actually. So this is max, and then you have 1, 2, and 3 here, and then you have 1, 2, and 3 here, right? So the max of 1 and 1 would be, for example, 1. The max of the max of 1 and 2 would be 2. The max of 1 and 3 would be 3. The max of, for example, 2 and 1 would be 2. The max of 2 and 2 would be 2. The max of 2 and 3 would be 3. The max of 3 and 1 is 3. The max of 3 and 2 is 3. The max of 3 and 3 is 3. So this is called the operation table for the operation. For example, in this particular example, we can call it the operation table for the operation table for the operation, for example, max in this case, right? Now in the text there is a bunch of things. I mean, there is the max of 1, 3 is equal to 3. 1 and 3 is equal to 3. The max of 1, 2 and 3 is equal to, the max of 2 and 3 is equal to 3. And the max of 1 and 2, max of 1 and 2 is equal to 2. But they have written these three, basically, they have written these, oh, I guess that's why they have written that. So, okay. So here we have the max of 1, 3. If you write the max of 1, 3, that is basically 1, 3 would be basically the first element. You take it from this column, which is basically you take your 1 from here, meaning that this 1 comes from here, right? And then the 3 comes from, and then the 3 comes from here, which gives me basically is equal to 3, which is basically this 3 over here. So you can say that the max of 1, 3 is equal to 3. And also the max of 2, 3, and also the max of 2, 3, again, 2 you take it from here, and 3 you take it from here, that is equal to 3. And the max of 1, 2 is equal to 2. The max of 1, 2 is equal to 2. So what's important here is that, I mean, they have written this most probably so as to point out to the fact that you're not supposed to take these the other way around, meaning that, for example, when I write the max of 1, 3, if I take my 1 from here and 3 from here, that again gives me a 3. If I take 2 and 3 over here, that gives me a 3, and 1 and 2 over here, that gives me a 2. That means that in any order that I take it, I'm going to get the same number, meaning 1 and 2 is 1, and 2 and 1, 1 and 2 is, I'm sorry, 1 and 2 is 2, and 1 and 2 is 2, and 2 and 1 is also 2, right? So the order doesn't really matter because we are talking about the max of two numbers. Now, again, I didn't understand why they have written these three specific statements over here. But now there is some theory that basically there is some theory that we can go through, and we can probably forget about this part, because basically what I have found is that when something confuses you and there is no reason to understand it, you just have to forget about it, because you could get into places where you don't want to be. And so Now here we are basically we have 3 rows and 3 columns in the operation table with I and j. So you have basically 3 rows, and I suppose by rows they are referring to only this part. So if I want to count the rows here, I would have 1, 2, 3, and 4 rows, of course, over here. But these are the arguments of the max function, and these are again the arguments of the max function. So if I denote these as the arguments of the max function, and these also the arguments of the max function, then the output of the table is only these elements here, right? And this over here, you have 3 rows and 3 columns. You have 3 rows and 3 columns. With I and j, with I comma j as the entry of the table being maximum of ith and jth element of the set A. So let me write this down. So basically here we are having 3 rows and 3 columns, and 3 columns in the operation table. With I comma j, the entry of the table being being maximum of ith and jth elements of the set A. Being maximum of ith and jth elements of the set A. Right? And this maximum is refers to this maximum over here, of course, right? Because I didn't understand this first. So so this can be generalized for general operation. This can be generalized for a general operation, star basically as an operation on the set A. Now if A is equal to this set, which contains, if A is equal to this set, which contains A1, A2, A3, all the way up to A of n, right? Then the operation table will be having n rows and n columns. Then the operation table will be having n rows and n columns. N rows and n columns with I comma jth entry being being A of I star A of J, right? So A of I star A of J. Conversely, so you can say conversely, given any operation table having n rows and n columns, given any operation table having n rows and n columns. Okay, so I made a mistake here. So you can say that conversely, given any operation table having n rows and n columns, with each entry being an element of A is equal to A1, A2, A3, all the way up to A of n, we can define a binary operation. We can define a binary operation. We can define a binary operation star on the set A, which is the Cartesian product of A to A, given by A of I star A of J is the entry in the ith row, is the entry in the ith row and jth column of the operation table. In the operation table, right? Now, one may note that, so this is also important and interesting, and that is, one may note that 3 and 4 can be added in any order. One may note that 3 and 4 can be added in any order, right? And the result is the same. And the results would be the same. That is 3 plus 4 is equal to 4 plus 3. Right? So what that means is that if you take addition as a binary operation on some set containing these two elements 3 and 4, if you take 3 plus 4, meaning that if the binary operation is done in this order, meaning that, for example, this is the ith element, this is the jth element, and the ith element is added to the jth element, and so you will get a 7 over here. Now again, if you get the jth element and Now if I take this element as the jth element and take this element, or I'm sorry, if I take 4 as the ith element or 3 as the jth element, the other way around, and then again do the same operation on them, I'm going to get the same thing, because in addition, order doesn't really matter, right? And that's basically what we saw basically in the previous table, that the max function gives you the max of two numbers, and it doesn't matter in which order you enter your numbers, whether you enter your whether you enter your basically a of I first or a of j first, you're going to get the same thing basically. So so one may note that basically 3 and 4 can be added in any order and the results would be the same, right? But subtraction of 3 and 4 in different orders would give different results. But subtraction of 3 and 4 in different orders would give different results. That is, 3 minus 4 is not equal to is not the same thing as 4 minus 3. 3 minus 4 is equal to -1, and 4 minus 3 is equal to 1. Similarly, in the case of multiplication, multiplication, of 3 and 4 order is immaterial. Order is immaterial, but division of 3 and 4 in different orders, division and 3 and 4 in different orders would give different results. Would give different results. Thus, addition and multiplication of 3 and 4 are meaningful. Thus, addition and multiplication of 3 and 4 are meaningful. Okay, so then you can say that thus the addition of multiplication of thus addition and multiplication of 3 and 4 are meaningful, meaning that in the reverse order they work as well and you have no problems. But subtraction and division of 3 and 4 subtraction and division of 3 and 4 are basically meaningless. For subtraction and division, division, we have to write subtract 3 from 4. For example, subtract 3 from 4, or subtract 4 from 3, or subtract 4 from 3, or divide 4 by 3. And this leads to the following definition. So definition number 11. We have a binary operation star on the set X is called commutative. A binary operation star on set X is called commutative. If A star B is equal to B star A. For every A and B belonging to X. So as an example, let's say that we have example number 34. Example number 34, we have show that addition basically addition on set R, and addition and multiplication on set R are commutative binary operations, but subtraction and division are not commutative. Subtraction and division are not commutative. Right? So as a solution, we can say that since A plus B is equal to B plus A, since A plus B is equal to B plus A, and A times B is equal to B times A, for every A and B belonging to R, then you can say that addition, and multiplication are commutative binary operations. Right? However, subtraction is not commutative. Subtraction is not commutative. Since 3 minus 4 is not equal to 4 minus 3. Similarly, 3 divided by 4 is not equal to 4 divided by 3. Shows that division is not commutative. So that is basically example number 34. The next example that we have is example number 35. Example 35, which is show that star, basically the operation star on the set on the set of real numbers, show that star on the set of real numbers defined by a star b is equal to a plus 2b, a star b is equal to a plus 2b is not commutative. Okay, so about this question. Okay, so here what we can do, basically we said that the definition that we had was that basically some operation star is said to be an operation on some set. Let me write down the exact definition that we had. So we said that the binary operation star on a set A is a function. We said that a binary operation star on a set A is a function which is basically star the Cartesian product of A and A into A, right? That means that in this function, what happens is that the domain of the function is the Cartesian product of the set that we are talking about, and then the codomain of the function is A, the set A itself. If that happens to be a function, then star is said to be a binary operation on set A, right? So we denote star of A comma B, as basically A star B. That is basically the definition that we have. Now over here what we have is that basically we want to show that star, basically a binary operation on the set of real numbers defined by A star B is equal to A plus 2B, is not commutative. So you can show that, for example, let's take for example one element or two elements of the Cartesian product of R and R by itself. Okay, so now suppose that I take 3 and 4. I wanted to give you this example, but it didn't work out too well for me. So suppose that I take, for example, 3 and 4, meaning that, for example, I take the ordered pair that I take in basically in the set, the Cartesian product of R and R is going to contain all of these ordered pairs, for example 3, 4, 2, 5, and there is an innumerable number of such ordered pairs in this set, because it's the whole of basically real numbers by the whole multiplied, and all of the relations that could exist between all of those elements with the whole of real numbers. So you can imagine that you get an infinite number of such pairs. Now suppose that I take this pair here, 3, 4, and if I do so you know that 3 star 4 is equal to basically, this becomes your A, this becomes your B. So you have 3 plus 2 times 4, which is equal to 3 plus 8 is equal to 11, right? And 4, and also you can write 4 basically star 3, that's equal to 4 plus 2 times 3, which is equal to, 2 times is equal to 6, 6 plus 4 is equal to 10, right? Now showing that the operation is not commutative. That the operation is not commutative. Now, as another, basically based on what we saw here, we can say that if we want to associate 3 elements of a set X through a binary operation on X, we encounter a natural problem. So if we want to associate 3 elements of a set X, 3 elements of a set X through a binary operation on X, through a binary operation on X, we encounter a natural problem. And the expression A star B star C the expression A star B star C may be interpreted as A star B star C, A star B star C, or A star B star C, A star B star C, and these two expressions need not be the same. Meaning that depending on what sort of binary operation you choose to have, then these two expressions, of course, could be the same, could be different. You don't really know what's going to happen. There is no way to know. And these two expressions need not be the same, right? For example, 8 minus 5 minus 2, 8 minus 5 minus 2 is not the same thing as 8 minus 5 minus 2. So this is basically 8 minus 5 is equal to 3, 3 minus 2 is equal to 1. This is 1, and this is 5 minus 2 is equal to 3, 8 minus 3 is equal to 5. Right, so 1 is not equal to 5. Therefore, association of three numbers 8, 5, and 3. Therefore, association of the three numbers of the three numbers 8, 5, and 3, 8, 5, and 3 through the binary operation subtraction, the binary operation subtraction is meaningless. Is meaningless unless bracket is used. I don't know what is meant by unless bracket is used. Right, the text says unless bracket is used, but I don't understand the meaning of this part, what they mean by this. But in case of addition, in the case of addition, 8 plus 5 plus 2, 8 plus 5 plus 2 has the same value, whether we look at it as as 8 plus 5 plus 2, or as 8 plus 5 plus 2. Thus, association of 3 or even more than 3 numbers through addition is meaningful without using bracket. Now, I don't understand. I see. Well, now we will see about the bracket thing. I don't understand it completely right now. So you can say that thus association of 3 or more than 3 numbers through addition is meaningful without using bracket. Right? This leads to the following definition. And this leads to the following definition, which is definition number 12. Definition number 12. A binary operation star basically on a set A is said to be associative if A star B star C is equal to A star B star C. For every ABC belonging to A. For every ABC belonging to A. Right? So this would be called a binary operation star on set A is said to be associative. So we talked about the commutative before. Now this is the associative part. Is said to be associative if A star B star C is equal to A star B star C for every ABC belonging to A. Now in the next video we will take a couple of examples, and so I'll see you in the next video, and thank you.